work by a varying force. Remember that our definition of work, that is, work equals the force times the distance times the cosine of the angle between them, was what I like to call naive. It requires the force not to vary during the motion. But of course, many forces depend on where they act and change as the object moves. So we need a new technique, or rather, we need to extend an old one. We're going to pretend that we can break the motion up into a lot of little steps dx so small that during any given one of them, the force can be considered constant. That is, we'll say that instead of having a full-on path like this, I'm going to break into lots of little steps so small that even though the force is varying, it doesn't change very much during any given one of them. For simplicity, we're also going to assume the force points entirely along or entirely opposite to the motion so that we can avoid the cosine theta factor. As long as the angle was constant, we would be okay, but it just makes things complicated without adding any real insight. If we do this, then we can just, quote unquote, add up all those little bits of work, which in calculus is written as that the total work would be the sum of all the little works. That is the sum of f dx, keeping in mind that f itself is a function of x. In this class, it's very important to understand you are not expected to use calculus. They don't ask you to do any symbolic manipulation using calculus. This is presented just for completion's sake. But what the committee does expect you to know is that on a graph of f versus x, the work is the area trapped. You should probably recall that we did something similar during our chapter on kinematics, where we said that if you had, let's do it this way, if you had a VT graph and someone told you that the object traveled like along with a velocity that changed like this, and you said, well, how far did it travel between this moment and this moment, you would have figured out the area of that. And the delta x is the area, what I like to say, trapped by the curve. So what we're saying with our new calculus is that when we say that we have the work is integral f dx, it tells me that the vertical axis is f, and that the horizontal axis is x. And that if I then had something which had a force that did something like this, and I want to know the work between two moments, here and here, I would, again, just find their area. And the work would be the area trapped. In other words, because the equation can be written in the same form, the calculus says it would have to have the same behaviors. That work is the area on a force-distance graph. For example, the force on the left jumps between three constant values. It starts at 5 newtons, it drops to 2 newtons for a little bit, and then it jumps back up to 7 newtons. The work done from 0 to 10 meters would just be the area of the blue rectangle and the orange rectangle and the green rectangle. That is to say, 5 times 4 plus 2 times 3. Whoops. That was weird. Plus 7 times 3, or a total of 47 joules of work. As with displacements, areas below the horizontal axis are considered to be negative. And again, that's not anything deep. We're just saying if we look at our graph, our height is minus, in this case, 3. So for the force shown, if we want to get between 0 and 6 meters, we would take this area, which is a triangle, which is 1/2, obviously, times its base, which is 6 meters, times its height, which is minus 3 meters, or minus 9 joules. Notice that this is consistent because the work, remember, is going to be the change in energy. So if this was something moving on a horizontal surface, the energy being changed would be kinetic, and this would say the object would be getting slower since we're doing negative work on it. So delta K is negative, so it's getting slower. And that makes sense because the force is also opposed to its motion. It's moving from 0 to 6, but the force is negative, pointing back the other way. So it gets slower. So this is all very consistent. It's just a way of sort of visually quickly identifying it. How much work in joules is done moving the object from x equals 0 to x equals 9 meters? Well, remember that the area of a triangle is 1/2 the base times the height the base is 9 meters, and the height is 6 newtons, so we get 27 joules. Notice that that was going from 0 to 9. If, on the other hand, we had gone from 9 to 0 with the same force acting, then we would have had an alternate thing, and we'd say it's still a half base times height, but now the base would have been minus 9 because I'm going against the usual way. And so we get minus 27 joules, which is what we'd expect. All right, that going the other way, this force would be resisting that, so it should give us negative work.